Welcome to my YouTube channel. In today's presentation, we will talk about ferroelectric field effect transistor. By introducing ferroelectric layer, leakage current can be appreciably reduced at high temperature. Ferroelectric material exhibit high dielectric constant, polarization, and hysteresis. My dear students, if you are searching a new domain area for your thesis, then the ferroelectric field effect transistor is the best option. You can design ferroelectric field effect transistor and ferroelectric tunnel field effect transistor. Both are the good option in ferroelectric domain. There are a number of advantages of using ferroelectric material. It will reduce the leakage current, improve the subthreshold slope of the device, and many more. Let's start. Ferroelectric field effect transistor. Piezoelectric and ferroelectric materials are widely used in many areas of technology and science. The sensor based on piezoelectric effect transform mechanical signal into electrical signal and are used as a accelerometer and for measurement of pressure and vibration. Next, we will discuss about the basic concept of ferroelectric material, that is ferroelectric hysteresis loop. I know it is boring, but you must know if you are thinking about to work on ferroelectric domain. I have one PDF on that. If you want, I can share with you. The most important characteristics of ferroelectric material is polarization, reversal, or switching by an electric field. Ferroelectrics are a special type of polar materials where spontaneous polarization possesses at least two equilibrium states. That is, the direction of spontaneous polarization vector may be switched between those orientation by an electric field. On seeing in the figure, you can notice down there are two value of spontaneous polarization, that is plus PS and that is down. It is not mentioned. You can note down that this is the minus PS value. At small value of alternating electric field, the polarization increases linearly with the field amplitude. This corresponds to the segment AB in the figure. In this region, the field is strong enough to switch domain with unfavorable direction of polarization. In this region, the field is not strong enough to switch domains with unfavorable direction of polarization. You can also see in the figure point A to B. As the field is increased, the polarization of domain with unfavorable direction of polarization will start to switch along direction that are cristographically as close as possible to the direction of the field. Rapidly increasing the measured charge density from the segment B to C, you can notice down in the figure. Once all the domain are aligned at point C, the ferroelectric again behave as a linear dielectric and the polarization will increase linearly from point C to point D. When the field strength start to decrease, some domains will backswitch, but at zero field the polarization is non-zero at the point PR, that is this one. To reach the zero polarization state, the field must be reversed at point F. A further increase of the field in the negative direction will cause a new alignment of dipole and saturation at point G. In the simple language, we can say that if you are increasing the electric field, the polarization start increase linearly from the point A to B, then after B to C. At low electric field, the field is not strong enough to switch domain with unfavorable direction of polarization. But if you are increasing the field, the polarization will switch to the unfavorable direction of polarization. When the field strength start to decrease, some domains will backswitch, but at zero field, the polarization is non-zero. This one, at zero electric field, the polarization is PR, that is non-zero. To reach at the zero electric field, the field is backswitched from PR to the point F. After that, if you are increasing the field in the negative direction, a new alignment of dipole, that is from point F to point G. After that, the field strength is then reduced to zero and reversed to complete the cycle. As already mentioned above, the value of polarization at zero field is called remnant polarization, that is PR, when the electric field is 0. The value of the PR lies between 0.001 to 1 C per meter square. The field necessary to bring the polarization to 0 is called the coercive electric field, that is EC, that will shift the PR to the 0 at point F. The value of this coercive electric field is approximate equal to the 0.1 to 10 MB per meter. Next is the introduction of the ferroelectric. Ferroelectric dielectric crystal which show a spontaneous electric polarization, and the direction of the polarization can be reoriented by an external electric field. In ferroelectric memories, direction of spontaneous polarization is used to store digital bits. One of the characteristics of ferroelectric memories is non-volatile, electrically switchable data storage device can be implemented. Typically implemented as a capacitor consisting of the ferroelectric film in between the two conductive electrodes. These are the application and the characteristics of ferroelectric memories. Voltage pulse applied to the cap determine the polarity 0 or 1. For readout, another voltage pulse is applied that determine whether or not polarization switch direction. Data readout in a ferro field effect transistor is non-destructive. Ferro field effect transistor has both memory and the logic function. Ferro field effect transistor is similar to MOSFET. The gate oxide is a ferroelectric material in case of ferro field effect transistor. Ferroelectric memories are based on the MOS transistor and one capacitor approach. We will discuss about in the next slide. Transistor is separated by a thick dielectric layer from ferroelectric cap. Next is the principle of ferroelectric field effect transistor. A structure proposed for improving the subthreshold slope and the on-state current of a field effect transistor is the ferroelectric field effect transistor. The ferroelectric field effect transistor shows excellent features as an integrated memory such as non-volatile, better scalability, higher read-write speeds, lower dissipation powers, higher temper resistance, and higher radioactive tolerance. Figure show the conventional ferroelectric structure. The first one, A, is the dynamic random access memory, DRAM. Second is the ferroelectric random access memory, that is one transistor, one capacitor approach. And third one is the most important, we will discuss about this in the next slide, ferroelectric field effect transistor, in which a gate oxide is replaced by a ferroelectric material or insulator. Ferroelectric field effect transistor. By replacing the conventional insulator with a ferroelectric insulator of appropriate thickness in the MOSFET, an effective negative gate capacitance can be obtained in a MOSFET. Figure show a schematic representation of a negative capacitance field effect transistor. Due to the negative capacitance at the gate of the MOSFET, a step-up voltage transformer effect can be observed. This amplifies the gate voltage and subthreshold swing to less than 60 mV per decade is obtained. This structure proposed for improving the subthreshold slope and the on current of a field effect transistor in ferroelectric FET. The biggest challenge of the negative capacitance field effect transistor is the identification of appropriate ferroelectric material that yield a low subthreshold slope swing and minimum hysteresis at room temperature, and the integration of that material into the conventional CMOS technology is also a very important factor. Figure shows the charge motion in a ferro field effect transistor during one cycle of operation. When the gate voltage is greater than the capacitor voltage, polarization vector P is directly towards silicon. Then accumulation of electrons in the N channel in the on state. But when the Vg is less than Vc, capacitor voltage, polarization is directly opposite and the electrons are depleted in the channel region. Non-destructive readout sense the source drain resistance. Ferro field effect memories are non-volatile, non-destructive readout and the compact cell design. You can see in the figure A, the polarization vector E is directly towards the silicon material. This will result in an accumulation of electron in the channel in the on state. But when the gate voltage is less than minus Vc, polarization is you can see in the figure B, polarization is directly opposite to the electrons are depleted. This is the basic concept of ferro field effect transistor. A stack of metal ferroelectric semiconductor is required in ferro field effect transistor. But there are a number of challenges in interfacing silicon and the ferroelectric material. First challenge is lattice mismatch must be as small as possible. Second, chemical reaction and intermixing should be minimized. Third one, number of interface states should be less than 10 to the power 12 electron per volt per centimeter square. Fourth one, formation of low K dielectric should be avoided. Only few perovskite oxide are suitable for growth on silicon material. Different design of ferroelectric structure. Alternative gate stack layouts and various buffer layer configuration have been developed. First one is the MFS metal ferroelectric semiconductor field effect transistor. We have already talked about the metal ferroelectric semiconductor field effect transistor. Another technology, another structure is metal ferroelectric insulator semiconductor MFIS field effect transistor structure. Third one is metal ferroelectric metal insulator semiconductor field effect transistor. And the last one is MFABO3, that is ferroelectric on a conductive oxide. This means no silicon is used. There are different design structure. First one is the MFS structure, metal ferroelectric semiconductor. Second one is metal ferroelectric insulator semiconductor structure. Third one is metal ferroelectric metal insulator semiconductor field effect transistor structure. And the last one is metal ferroelectric high resistive conductive material as a gate structure. In the next slide, we will talk about on these structures. First one is the MFS structure, metal ferroelectric semiconductor gate structure. In MFS structure, a ferroelectric material is used in the gate stack as shown in the figure. When a gate voltage is applied, the polarization of ferroelectric material in the gate stack increases the effective gate voltage seen by the channel. In MFS structure, ferroelectric material is directly on silicon. The intermixing from silicon to perovskite lead to the degradation of the ferroelectric properties. But there are a number of advantages of using this MFS structure, such as high density, simple circuit, non-destructive readout, and PVDF thin film, such as low cost and the low thermal budget. The second structure is MFIS, metal ferroelectric insulator semiconductor gate structure. Due to its metal ferroelectric insulator semiconductor gate structure, the FET is called MFIS FET. Buffer or insulating layer is present between the ferroelectric and the silicon layer. The effect of charge injection can be minimized by employing an engineering buffer or insulator sandwich between the silicon and peroxide layer. Buffer layer reduces the problem of intermixing silicon and the ferroelectric material. Next is the gate oxide is comprised of two capacitance in series. First capacitance is due to MFI and the second is due to the gate structure. To avoid interface damage suffering during the device preparation at high temperature, the insulating layer is present between the ferroelectric and the semiconductor. And one more, I missed it, buffer layer weakens the electric field across ferroelectric. Next ferroelectric structure is MFMIS FET structure, that is metal ferroelectric metal insulator semiconductor gate structure, in which a floating metal electrode inserted between the ferroelectric and the insulator layer provides a highly ferroelectric thin film without damaging the SiO2 gate layer. The gate stack is called MFMIS structure. From the structure, you can notice down that we have inserted a floating metal between the ferroelectric and the insulator layer. When applying a small voltage to this structure to avoid breakdown in the SiO2 film, the electric field in the ferroelectric reverses only the partial polarization, yielding insufficient polarization hysteresis. In MF-MIS structure, the polarization can be fully reversed by reducing the polarization charge, thus improving the characteristics of the device. The polarization and the thickness of the ferroelectric as well as the thickness of the SiO2 film should be adjusted to allow for sufficient voltage application to the SiO2 Si structure. There are some advantages of this structure. First one is MF-MIS structure reduces the intermixing problem between the ferroelectric and the silicon material. Second one, it acts as a voltage divider. Third one, gate voltage is divided according to the capacitance ratio of MIS and MFM capacitor structure. Capacitance of MIS diode should be large enough to allow the polarization reverse of MFM, that is metal ferroelectric metal capacitor. Relatively large voltage necessary to switch the ferroelectric capacitor in case of SiO2 insulator. The last structure is metal ferroelectric on a conductive oxide. Source drain channel is replaced by a conductive oxide in case of this structure. These have similar growth condition as ferroelectrics. The aim is to modulate conductivity of the conductive oxide by the polarization of ferroelectric. Now let's go to the code. Again, start from the command do atlas. The main reason of using ferroelectric layer, it will reduce the leakage current when the device operates at high temperature. Ferroelectric material exhibit high dielectric constant, polarization and the hysteresis. Let's go for the example. Start from the meshing. Again, the multiplying factor is 1. X meshing is start from the 0 and end at the 5 micrometer. I am applying the ferroelectric concept to the bulk MOSFET. Y meshing is start from the minus 0.131 micrometer to the 0 micrometer with different spacing from 0.015 to and at 0.2 micrometer. Please note down the meshing and every step very carefully. Next, I have defined the region number with the material. The first region is silicon. I have taken y minimum 0. It will automatically take the maximum value of the y-axis, and it also includes x-axis from minimum value to maximum value. Next is the region 2, that is the oxide. I have mentioned the positional parameter from y minimum minus 0.001 to y maximum 0. Region number 3 is used for defining the ferroelectric material. I have defined the ferroelectric material with the name ferro, and in the code I have defined user.material with the positional parameter in the y direction. Region number 4 is again oxide material, that is SiO2, with their positional parameter from the y minimum minus 0.131 to minus 0.101. Next, I have defined the electrode at different terminal. First, I have defined the electrode at source terminal with their positional parameter. Next, I have defined the electrode at drain terminal with the positional parameter. After that, I have defined the electrode at gate terminal with the positional parameter, and I have defined using the command top. Next, I have defined the electrode at the substrate terminal with the command bottom I have used. Next, doping uniform. In the channel region, I have defined 3E16. In the drain side and source side, I am using Gaussian distribution concentration. If you don't know how to define Gaussian concentration, you have to follow my previous videos. I have already explained how to define Gaussian distribution concentration. I have mentioned that in the drain side and the source side, I am using the Gaussian concentration with their positional parameter. Next, I have defined the ferroelectric material model region 3 ferro model. Next, I have defined the new material ferro with the material region 3 material ferro user.group insulator user.default oxide ferro.ps 0.5 E-6 ferro.pr 0.4 E-6 ferro.ec 1 5 zeros and the ferro.eps 10. Ferro.eps is represent the dielectric constant of the ferroelectric layer. Ferro.pr represent remnant polarization. Ferro.pr represent spontaneous polarization. In the hysteresis loop, I have explained about remnant polarization PR and the spontaneous polarization PS. And EC is the coercive electric field that is required for the polarization. Next, I have defined the gate function and the channel mobility. I have defined the contact and polysilicon. One more material property, that is the mobility of the electron, that is 800. I have defined in the code. Next, I have defined the method, neutron and autonomous. Next, I am applying the voltage at the different terminal, drain, gate and source. First, I have applied solve drain voltage at 0.1 volt. Next, I have saved the log file with the name Ferro-EX02. Next, I am applying the gate voltage from 0 to 8 volt with the step voltage 0.1 volt. Next, I have defined the frequency 1 megahertz. This is used for the forward sweep. For the reverse sweep, you have to define again the ferroelectric field in the negative direction. Again, applying the voltage at the gate terminal from minus 0.1 to minus 8 volt with the gate frequency 1 megahertz. Next is the Tony plot command for the structure and the log file. You can view the log file and the structure file using Tony plot. If you run this program, you will get the two files. One is the structure file and one is the log file. This is the structure file. Hello my dear friend, this is the structure file. From the structure file, you can notice down that this is yellow one is the ferro material. This is the drain and the source content. This is the SiO2 material. This is the silicon material. The thickness of the gate electrode is very less. If you want to see that, then zoom it. By zooming the device, you can see that SiO2 is present between the silicon and the ferroelectric material. So that this is a MFIS structure, metal ferroelectric insulator semiconductor gate structure. And this is the log file. You can see the hysteresis. That is from the lower waveform represent 0 to plus 8 and the upper will represent drain current in the reverse direction from 8 to 0 volt. One more thing, I have applied ferroelectric material in FeFET also, internal field effect transistor. In this presentation, I have only talked about ferroelectric field effect transistor. One of my publication is under process on ferroelectric tunnel field effect transistor. As I got the acceptance of this publication, I will discuss my ferroelectric FeFET code with you. I have already told you that if you are searching a new domain, then ferroelectric is best option for you. For this, you have to focus on three important parameters, that is remnant polarization, spontaneous polarization, and the coercive electric field. And the last one is optimization of ferroelectric field effect transistor. Short retention time originates from the fact that the dielectric capacitor is connected in series with the ferroelectric capacitor. Under short circuit condition, direction of the electric field in ferroelectric is opposite of that polarization. Second, leakage current between ferroelectric and buffer removes these charges. Hence, the stored data cannot be read out. To minimize polarization field, buffer layer capacitance must be as large as possible. To optimize the ferroelectric field effect transistor, leakage current must be reduced. To optimize it, it is necessary to make the ferroelectric film smaller and thicker than the buffer. Otherwise, most of the external voltage will be applied to buffer layer and no reverse polarization will be possible. Too thick ferroelectric makes the operation voltage too high. You have to must take care of that to optimize ferroelectric field effect transistor. This is